how far this thing stretches. Not very far, it's headed to the spot. Okay, so my name is Paul. I'm from the University of Manchester in the UK, and I'm part of an interdisciplinary team working on statistical methods and software for making quantitative measurements from planetary surfaces. We're part of an interdisciplinary team involving planetary scientists and imaging scientists. I'm from an imaging science background myself. First question I'll answer is, why are we doing this? Well, we want to automate the process of analysing satellite images because there are simply so many of them now. It's almost impossible to get enough experts to analyse each of the images. So what I'd like to do today is give you an overview of what we're trying to achieve, how we're doing it, and how far we got in terms of the progress and the success of our most recent results. So we'll start off with an overview. What we want to do is make quantitative measurements from, in particular, high-rise images, so Martian images from the high-rise project. So the type of thing we like to do is estimate surface areas of different terrain types, or counts of features such as how many craters are there in this particular area. There are a couple of inputs into this system. It's a supervised learning system which is flexible enough to allow a planetary scientist to select the type of features and the type of terrains they would like to analyse. So, for example, we may feed in images of Martian dunes, different types of dune fields, Martian spiders, you know, the CO2 eruptions that we see. And we provide images of these, expertly annotated images, to say to the computer, this is what we'd like to find. And we also want to be able to input previously unseen images, so images that require measurements to be taken from them, hence the question mark. So this is stuff we don't know what's in there, so a person doesn't have to look at it. And the outputs, primarily we want quantity estimates, so surface areas, counts of features, but we need more than that. For scientific measurements to be useful, we need more than just the measurement itself. We need to understand the measurement accuracy, and we want to be confident that we can compute the measurement accuracy on a measurement by measurement basis. We also would like to have some kind of goodness of fit measure, some kind of figure of merit that indicates to the user how successful or otherwise the analysis has been. Now, I've highlighted these two things in red at the bottom because competing algorithms, and there are existing computerized methods to do things like this, but none of them, in our opinion, are scientifically useful for making measurements because they do not provide the error estimates and they do not provide the goodness of fits success measures. So the type of things we want out of this is the surface area, what kind of surface area is covered by whatever terrain, plus or minus the error bar, and some goodness of fit. So how do we do this? Well, we have a training phase, and during the training phase, we take the expertly annotated images and we turn those into histograms. I'll talk a little bit more about the histograms in a couple of slides, but they encode the distribution of the patterns you find indicative of different terrains. Now the next thing we do is we extract the constituent components of those distributions. So we find the common things within those distributions that says, this is this type of terrain. And again, I'll talk about this a bit later. And then we group those components together into different classes of terrain, different classes of features. So we'll have a bunch of components that describe dunes, a bunch of components that describe craters and so on, or whatever the user wants to describe. Now, during the analysis stage, we start again by converting the unseen image into a similar histogram. And then we use a regression technique based on likelihood, which is optimized using an algorithm called expectation maximization. And this basically takes what we've learned previously and fits it to the new unseen data. And you find through doing this that the parameters of the model fits are proportional to the measurements we want to make. So we fit the model and we get the measurements out at the same time. And to get the error estimates, we use a technique known as error propagation, which any physicists in the room, you may be familiar with error propagation. It's a standard technique. And we also compare the statistical model we make with the incoming data to look at the differences between the training data and the incoming data to find a goodness of fit, to create a goodness of fit score. So in more detail, starting with the histograms, we want the histograms to encode the structure of the underlying terrain. So we do this by looking at the light-dark patterns within the image. So we'll divide the image up into lots of circular windows. Within each circular window, we'll take a subsample of the pixels and we'll take them in pairs and we'll look at the brightness difference between the pairs. And this gives us a fairly low resolution but robust way of describing the underlying structure, taking out some of the illumination conditions. And you can encode this as a binary string, i.e. this is brighter than that, 1, 0. Now, some features are connected, such as, let's say you look at the crest of a sand dune. Along the length of the crest of a sand dune, you get similar light-dark patterns. So we've grouped those together into what we call blobs. And you can do a similar thing for, say, the uniform space. If there's uniform space, you've got a similar light-dark pattern within them, you blob them together. So you end up with this blob representation that encodes light-dark patches to describe the structure and the size of the blob. Now, the histograms are constructed by assigning each histogram bin a particular blob type. And then you record the frequency of occurrence of that type of structure across the terrain. Now, from this point forth, we're only going to talk about histograms because the analysis only needs histograms from this point forward. But bear in mind that all the histograms are ultimately derived from image data in this kind of blob format. Now, what you'll find is if you analyse a whole bunch of sand dunes that you think are kind of similar, in reality, a given sand dune field will contain slight variations in size, orientations, slight differences in morphology. So what we would consider similar through our eyes might not be considered similar statistically. So the first thing we do with these histograms is we take numerous examples from each terrain type and we try to pin down the common factors, the common constituent components of the histogram. So for example, let's imagine these histograms were all dunes. And we can use an independent component analysis to extract the common features. So you'll see we've got 3 distinctive shaped probability distributions that can be combined linearly to describe all of these histograms. So our training algorithm is extracting these probability distributions to be recombined later to describe future data. And we do this for all the different terrains, all the features we would like to measure. So we'll have some components for dunes, craters, spiders, and so on and so forth. So we describe the entire distribution of the data. Now, I said about other methods, limitations of other methods. In contrast with other methods, there's some popular things out there called support vector machines, random forests, boosting algorithms, and certain architectures of neural networks. They do not learn distributions. To simplify, what they do is they just learn a decision boundary. So they will draw a line in the sand and say, on this side, it's bark and dunes. On this side, it's all of the different types of dunes. So these techniques, they just learn a line in the sand. So bear that in mind, that'll come in later.
Can I ask a question before we proceed?
Sure.
So the histogram that we're talking about, the y-axis is the number of pixels and the x-axis is the different brightness levels?
The x-axis is, each bin is a different type of blob that we described earlier. So the adjacency on the x bins is fairly meaningless. It is more of a bar chart than a histogram in a sense, but the y-axis is frequency. The x-axis, each bin is a different type of blob, it's a different type of pattern. Okay. So when it comes to the analysis stage, we convert the unseen images that we like to analyse into histograms and we feed them into our software. Now, let's say this is a chunk of histogram from some unknown image. And we'd like to know what parts of this, how much of this image is composed of different things. So the first thing we want to ask is, how do we describe this in terms of the histograms we have seen previously? And we use an expectation maximization algorithm, which optimizes the likelihood on the screen here. For those of you who like mathematics, this is known as extended maximum likelihood, and it's usually attributed to Enrico Fermi. You may have heard of him, he's a fairly smart guy. And what you'll find is you can estimate the quantities of the things you've seen before and how you would fit them and scale them and add them together to describe the new incoming data. So in this diagram, you'll see you've got the things we learned previously scaled, summed together to approximate the incoming data. And what we end up with is, if you look at, say, the blue integral, that is proportional to the measurements we want to make. If we multiply that quantity that we've extracted from the model fit, if we multiply that by the size of the blobs in our image encoding, you get your surface areas. So what you end up with is a statistical model that synthesizes the incoming data in terms of things that we have seen before. So we synthesize the entire distribution, and we also have the real distribution from the incoming data. Now, in contrast to other methods, the fixed decision boundary methods, they're far more simplistic. What they do is they take this line in the sand that has previously been drawn, and they will just plonk it on top of the incoming data, and they will say, everything on this side is bark and dunes, or everything on this side is craters, and they'll just count what's on one side of the divide. Now that does not take proper account of the potential overlap of the different distributions. As we can see at the bottom, our simulated histogram of the bark and dunes, that is overlapped with the red distribution and some of the yellow distribution. So you cannot just draw a line in the sand and expect it to work every time, because it won't. The other thing, the really important thing that I emphasised at the beginning was a measurement itself isn't of too much value. We need to know the accuracy of the measurements. And there are two sources of uncertainty in our approach. There's uncertainty in the sampled histograms of the data that's being analysed. It's a statistical process. Each of these histogram bins is going to be randomly perturbed slightly just through sampling noise. And we use the typical model for histogram bin noise, and that's Poisson statistics. So we have an idea what the noise is on the incoming data. We also have noise in the statistical model that we build, because ultimately it's derived from training data that was again sampled into histograms. So you've got a slightly more complicated thing where you've got scaled Poisson processes added together, but we still can compute what the noise characteristics are of the statistical model. Now, to go from that to error bars on the quantities and surface areas, we use error propagation. And what that does is it works on derivatives. You see how small changes in the inputs affect changes in the outputs. And you can create a whole covariance matrix doing this. So this is where we get our error bars from. Now, in contrast, the alternative methods, they typically evaluate things after the event. What they'll do is they will use something like a receiver operating characteristic curve, which tracks true positives versus false positives. In other words, it'll track the number of times it got something right versus the number of times it got things wrong. But to do that, firstly, you need to know the ground truth. You need some reference ground truth to see where your mistakes were. Also, an ROC curve is not an error bar. So this is not necessarily appropriate for making scientific measurements. Moving on to the goodness of fit, we'd also like some kind of figure of merit to say whether or not our analysis has been successful. And the way we do that is we look at the difference between the statistical model we build from the training data in comparison to the new incoming data. So if the green bars are the incoming data of the image being analysed, and the green triangles is the statistical model we have fitted to that data, there's going to be a difference between them driven by this Poisson noise. And if it's within limits, we know that's okay. But what happens if you enter an image that contains some features that you've never seen before, that weren't in the training set? That's going to leave outliers in the data. You need to be able to spot these. So this is a simulated example. If there are outliers, you've got peaks and troughs which you weren't expecting to see, which means the residuals are a lot larger. Now, you can use a standard statistical test. You can use what's known as a chi-square per degree of freedom test to check the model data residuals. And if it's behaving itself, you should come up with an answer of unity. You should get a goodness of fit of 1. If it's larger than 1, it means something's gone wrong, and it means you cannot trust the analysis. In contrast, alternative methods, because they just learn the line in the sand, they have no concept of a goodness of fit. It just simply doesn't exist. There's no way of telling from the output alone of the alternative algorithms that something went wrong when problematic data was entered. Our method will warn the users of problems. Alternative methods, they don't. It's kind of important. So that's all great in theory, but what about how well it works in practice? Well, we've tested this in a couple of ways. We've tested this with Monte-Carlo simulated histograms. So we've synthesized a whole bunch of histograms with known properties. And we have mixed combinations of those together to see whether we can extract measurements from them when we know what the answer is. And it works. In Monte-Carlo, it works. So the quantities we estimate are right within errors. The error predictions we come up with are matching the observed errors we see in practice, and the goodness of fit reaches the desired value of unity, and it works across all different quantities of data, different complexities of models. It just works. It's a new statistical technique that can be applied to analyze histogram data. Now, that's all well and good for synthetic histograms where the properties of the histograms are controlled. The real question is, how well does it work on Martian data when you encode the histograms using this block representation? That's the important thing. So what we did was we took a whole bunch of high-rise images. We've got some dunes, we've got some brain terrain, we've got some Martian spiders, we've got a whole bunch of things that we thought, these are interesting features people want to look at, let's see if we can learn these. And we grouped them into 10 groups of 3. And what we did was we simulated large quantities of Martian terrain with known surface areas to see whether we could then measure those surface areas. So we start with a mask saying this is what we want the terrain to look like, and then we take small tiles from the high-rise images and we smoothly composite them together, add additional noise to make them independent statistical samples, and we can create all kinds of terrains. I know that's not what you're going to see on Mars, but the point is, the textures in these bands are from genuine Martian terrains, and if we can measure the surface areas successfully, then that's a proof of concept. So, what about the results? Well, the plot on the left shows the percentage accuracy of our surface area measurements. The x-axis shows images in increasing size, and the y-axis is one standard deviation error as a percentage of the measurements. And as we can see, we get quite good accuracies on surface area measurements, less than 1%. And these are averages on some of the images where we're down to maybe 0.25% for certain image sizes, so we can make relatively highly accurate surface area measurements. Now, one of the big question is, do our error predictions match the errors we see in the data? They did in Monte-Carlo. Will they on the Martian data? Well, we're very, very close. The right-hand plot shows, again, size of the image on the y-axis with the ratio of the observed to predicted errors on the x-axis. So if it works perfectly, that should be a straight line of 1. As we can see, it isn't. It's typically between 2 to 3, but that is actually really, really, really good from where we started. When we started this, we were struggling to get in an order of magnitude with our predictions. And this is just about getting into the realms of usability. At the end of the day, when you put an error bar on a result, it's there to prevent over-interpretation. And if you get the error bar within a factor of 2 to 3, it's not great, but it's a good start. And let's remember, alternative methods don't even attempt to do this. Now, the goodness of fit also came out very close to unity between 1 and 1.2, which really isn't bad. Any of you who have done a regression or looked at chi-squared results, between 1 and 1.2, that means we're describing the data quite well. There are, however, limitations. The theory assumes that the histograms contain independent Poisson bins, and in real data, the bins are not completely independent of one another in terms of the noise process. And this is due to, we've investigated this and we found that this is due to localized spatial correlations. And this is what explains the factor of 2 to 3 out in our error predictions. However, with sparse subsampling or a calibration step, these could be ironed out. I'm showing you the raw results here for honesty, but we could sparsely subsample or calibrate these to get better results. The other limitation is with the encoding scheme itself. The Poisson blob representation that uses bright-dark comparisons, that is dependent upon the illumination. So as soon as the sun moves, the images look different because the shadows move. So we're limited at the moment to analysing images that have the same illumination conditions as the original training data. But we're thinking we can widen the net to other illumination angles by using a technique known as shape from shading. We've not tried this yet, but we think it has a good chance of at least making it more applicable. But at the end of the day, we've got lots and lots of images, so we can find lots of images at different orientations of sunlight. So it's not a showstopper. So in summary, we've developed a technique which can learn arbitrary terrains and features, and we can make quantitative measurements from future images based on what we've seen previously. And importantly, and what is unique, and we've looked, unique to our method, we can give data-specific error estimates, and we can give goodness of fit checks. So we are confident we can make genuine scientific I'll get that word out. Genuine scientific measurements using this method. The theory, the new statistics that we've come up with, that's been proven in Monte-Carlo, it works. The accuracy on Martian data sets, we can measure surface areas, some within a fraction of a percent. There are a couple of problems, as I said on the previous slide, but the key take-home message here is this work represents the only fully quantitative analysis method of this type. This is a world first. Not many people know about it. We're trying to again, I'm losing my words there. We're trying to publicise it at the moment. It's one reason why I'm here today. I'm claiming it's a world first, so I expect people to be critical. So many thanks for listening, and if you've got any questions, I'll take questions now. Thank you.
If I understand correctly, the result will be that you can say on a certain given surface, on a certain location, how many of the types of geographical phenomena appear. Is that right?
That is what we're hoping to get as the end result. At the moment, we have been making surface area measurements, but when it comes to translating those into feature counts, it's quite straightforward. For crater counting, for example, if you're populating a size frequency distribution, you know the area through pi r squared, what the area is of a certain size crater, so you can make the translation between surface area to feature counts. So there are ways of going from this to feature counts, but what you're saying is basically the answer is yes. We're working towards that, we can do that in principle, yes.
So, yeah, personally speaking, I'm in love with the statistics behind image analysis, but this question has haunted me for a long time. Like, this is kind of a very awkward question, but Facebook.
Yes.
Facebook can identify people's faces in the images that you upload and suggest you that this is your friend John.
Yes, yes.
Would you like to tag him? So if we have such sophisticated technology, why are we still struggling to just identify creators in a picture?
That's a very good question. And the answer is, if I go right back to the beginning, the two things highlighted in red. Most algorithms stop at quantity estimates. So in the case of Facebook's facial recognition, it stops at the point where it thinks it has a face. For scientific use, that is insufficient. We have added the additional bits that you need to make it useful for science, and that is the error theory to estimate how accurately our measurements are being made and some goodness of fit. About facial recognition, I read a paper recently. I can't remember.
It doesn't have to be facial recognition. It could be anything. Like there are software.
Well, the reason why we're struggling is because people who do pattern recognition in imaging science, they neglect the two things in red. That's the short answer. I sense from your face that's not a satisfactory answer, but we can talk about this afterwards if you like. But basically, alternative methods fail. Well, it's not so much that they fail, it's just the characteristics are hard to understand unless you have an error theory. So you need the error theory to do science. That's the take-home message.
It looks from the way that you have your histograms arranged that the blob types need to be closely related if they're adjacent to one another. Did I miss something?
No, you didn't miss anything. That's a good observation. The histograms that I've been showing in this presentation have all been for illustrative purposes. The real histograms we generate have many thousands of bins, and the adjacency between the bins is very complicated. It's not just a flat histogram. You actually have, for every pixel pair we choose in the representation, there is a binary dimension in the histogram. So you have these high dimensional histograms containing a great many bins. So the adjacency is complicated. But that's a good question, and this is slightly misleading in that respect. But yeah, thank you for your question. Any other questions? No? Okay, well thank you very much.